All right, so with related rates, I'm going to go through a kind of a summary here of related rates, and then I will do a specific example or two to kind of remind us of what it was we were working on. In a related rates problem, you're asked to find the rate of change of some variable. Maybe you're asked to find the rate at which the area of a circle is changing. Maybe you're asked to find the rate at which the length of a cable is changing. Maybe you're asked to find the rate at which the length of a shadow is changing. The bottom line is you're trying to determine the rate of change of a variable. And the reason it's called related rates is the rate of change of the variable that you're trying to find is related to the rate of change of a different variable. So for example, and we can do a specific question here. I don't want to do the textbook ones here dealing with x cubed plus y cubed, all that stuff. Let's take a look at a question like number 3. It says, how fast is the area of a square increasing? So if I stop right there, you're asked to find the ADT. That's what you're asked to determine. So that's a rate of change that you're asked to find. Now it says the side has a length that's growing at a particular rate. So you're given, I'll use S for side, ds dt is positive 0.8. So in any related rates problem, you're given a rate of change that you want to find, and you're given at least one other rate of change. Now, if you take a look at the first thing I'm saying that you need to do, you need to come up with an equation, and this is tricky to understand this language in this sentence, but it's important. You need to come up with an equation that relates the variables whose rates of change you either know or want to know. So in my example, and I just want to move it a little bit closer here, in my example, we have a rate of change we know that's d side length of square dt. We have a rate of change we're asked to find, which is dA dt. So the variables whose rates of change I know or want to know are these variables. These are variables whose rates of change we care about. So the first step, if you take a look at my summary here, the first step is what's an equation relating those variables? Well, so the area of the square is s squared. That's how you find the area of a square. I'm going to give you this sheet that you can use when you're working on these related rates problems throughout the next few days. I made a decision a couple of years ago that when it comes to exams, I would never give you a formula sheet like this, but instead any formulas that you needed would be given in the question. Okay? So this is just something that you can refer to. On the front side of it are formulas for two-dimensional figures. That means flat figures. And on the reverse are some formulas for some common F2. For some common three-dimensional shapes. Thank you. You're welcome. So on the front, you've got things like circles and squares and rectangles and triangles, and I would hazard a guess that most of you probably don't really need a formula sheet from any of those. There's also the formula for the area of a trapezoid. Your three-dimensional shapes on the other side include things like spheres and cones and cylinders, and when we get to the necessity to talk about it, we will. Things that I would just classify as regular solids. So there's my first step. What's an equation that contains the variables whose rates of change you know or want to know? We're done. A equals s squared. Your second step is to differentiate it. And what you're going to discover, particularly with some of the examples we do today and tomorrow and the next day, is the first step is the most difficult one usually. Coming up with the equation is not always going to be as simple as looking at your formula sheet and saying, oh, it's that formula. You're going to have to develop it somehow. So your second step is to differentiate everything with respect to time. This is probably what I would say is the simplest step here. The derivative of a with respect to time is dA dt. The derivative of s squared with respect to time is 2s ds dt. That's your second step. Any questions with the derivative there? Okay, your final step is to use this and maybe this a little bit to answer the question. Don't forget what we're trying to find in this question is dA dt, which means you need to have a number to put here and here in order to answer the question. Well, what does it say? It says when the side is 3 meters in length, well, that's s, and ds dt we were given as 0.8. So this is a pretty tame related rates question, really. dA dt equals 2 times 3 multiplied by 0.8. One of the things that you do need to really always be on the lookout for is to make sure you have consistent units everywhere. So if the side length were given in centimeters and the rate of change of the side length were given in meters per minute, you've got to reconcile that somehow by making them both the same type of unit. Anyway, whatever we get here, which I believe is going to be 4.8, but you can maybe run that through a calculator for me. It is 4.8. So you get dA dt is 4.8, and it's going to be meters squared per minute. You know, if this were a science class, I would be more interested in leaving the units in. The reason it's meters squared per minute is this is really 3 meters, and this is really meters per minute. But as the problems become more complex, leaving the units in makes it more confusing. So I would recommend that you just do the math. When you get to your answer, put the units that the answer should have. So step 3 was solve the differentiated equation for whatever it is you want to find. One final comment, and then I'll open it up for questions. I said that you are going to use this equation along with maybe this equation to answer the question. And I say that because sometimes instead of you being told that the side length is 3 meters, you might be told something like the area equals 9 meters squared. So you might have to use your area formula relating area and side length to find the side length using the area, which would mean just take the square root of 9 and you get 3. All right, let's open it up. Let me get my chat window open here. Does anybody have any questions you would like me to go over? Liam? 5? Certainly. We're talking textbook 5? So a stone is dropped in a lake, creating a circular ripple that travels at a particular speed. Now, if you have, I don't feel up to drawing nice circles today. If you have a circular ripple or a circular wave that's expanding outward, if I say that the ripple is traveling at 25 centimeters per second, then what that means is that the radius is growing by 25 centimeters per second. When you drop a stone in the water and that ripple travels outward, every point on that ripple, every point on that circular ripple is moving away from that point where the stone hit the water. So what we're really told here is dr dt is 25. And I guess I can put centimeters per second. It's not a bad idea to put the units in your list of rates of change. I told you at the beginning of this as a summary from last week's topic on related rates that your first step is come up with an equation relating the variables whose rates of change you know, like dr dt, and want to find. So when we finish reading the question, it says, what is the rate of change of the area? So there's one rate of change we're given. There's another rate of change we're trying to find. The variables whose rates of change we're talking about are the radius and area of the circle. So now I can use a equals pi r squared as opposed to the other one where I thought I could. A equals pi r squared. This is your first step. Right there, it's done. Second step is to differentiate everything with respect to time. So the derivative of A with respect to time is dA dt. Now pi, I mean there's three letters in this equation. There's A, there's pi, and there's r. A is a variable, r is a variable, but pi is a constant. It doesn't change. So we treat it as a constant. And when I differentiate a number times a variable to a number, I can use the power rule. I swing that exponent down. I drop one from the exponent. Of course, it's not necessary to write r to the 1. And then I multiply by the derivative of what's inside, which, since we're doing related rates, you're always going to have these d variable dt's popping up. Now it says, what is, I want to back up. That's the second step. The third step says solve the differentiated equation for what we're trying to find. And then below it, it says you're not allowed to put values for the variables until after you differentiate. So in most, I might say in 99% of related rates problems, you will find, except for this one, you will find stuff like when the volume is, when x equals 2, when the side length is 3. Those conditions, when, are talking about values of variables that you don't want to touch until after you differentiate. The word when, of course, in the English language can be changed to other things. This says after 4 seconds. So I could say when 4 seconds have elapsed. The only problem is we don't have a time here. There's no time variable, even though we've got a d variable dt. However, there's two workarounds for this. One of them is to say that since the ripple is traveling outward at 25 centimeters per second, then 4 seconds after it hits the water, the ripple will have traveled 25 centimeters and 25 centimeters and 25 centimeters and 25 centimeters. In other words, we could use something like speed equals distance over time in order to find the radius if the speed is 25 centimeters per second. And 4 seconds have elapsed. So just turning this into like a Science 9 or a Science 10 problem, 4 times 25, 4 centimeters per second times 20 times, 4 seconds times 25 centimeters per second gives you 100 centimeters. Now, is dr dt given in centimeters? Yes. The radius we just found is in centimeters, so it's all internally consistent with variables. So my dA dt, which I'm trying to find, will be 2 times pi times 25 times 100. I guess I'll put them in the order that they appear in the equation. R is 100. And then dr dt is 25, so we can multiply that all out. If you're interested in an exact value, which I would question what would be the big deal of that here. You would multiply the 2 and the 100 and the 25 and get 5,000, I think, pi. So if we multiply out the constants, you get 5,000 pi. This would be square centimeters per second. If you want to work out what the approximate value is, it's going to be, I don't know, 15,500 approximately when you multiply 5,000 by pi. But you can work on that. You can do that calculation yourself. $15,707 centimeters squared per second. One of the things I would caution everybody about here is you get this number, and this seems awfully big, doesn't it? It's a big number. When you do a related rates problem, the answer you get might not be something which is consistent with what you think it should be. You have to trust the math here. Is that okay, Liam? Okay. Any other questions anybody would like me to go over from this? Yep, absolutely. From the textbook. Yeah. So how fast is the length of a cube increasing when the volume of the cube is increasing at a particular length? So let's define our rates of change here. d volume dt is given to you. The volume is increasing, so dv dt is a positive thing. 144, and I'll put cubic centimeters per second. And then we want to find, I'll use L for length of the cube. Now, if you were to go to the formula sheet I've given you, a cube is what classifies as a regular solid. So examples of regular solids are things that can be cut, and anywhere along a certain axis they're cut, you get the same shape. So it's not perfect, but if you have a loaf of bread is almost a regular solid. Because when I put that loaf down, if it's unsliced and I start making slices, I understand the shape of the bread changes near the ends, but the shape of each slice is pretty much the same, right? So, as an illustration here, if I have this and it's a cylinder with a hole in it, this is considered a regular solid, because if I cut it here, if I take a really sharp mathematical knife and I slice it horizontally, anywhere I slice it along here, I'm going to get this same shape, right? It's going to be that shape. And the volume of a regular solid is always found by taking the area of the shape that's the same throughout and multiplying by the height or the length or the depth. I mean, it depends on which angle you're looking at this thing at. So when you take a look at this front face of this object has a particular area. I'm not too concerned about the fact that it's not a nice shape, but it has a particular shape. And if you can determine the area of this shape and then multiply that by that depth, you'll get the volume. Now, I'm going a long way to explaining how to find the volume of a cube. The volume of a cube is length times width times height, and since it's a cube, it's the length cubed. But what I'm getting at is that if I have a cube, it has a base that is a square, and it has a height that is equal to the length of the base. That's the only way I know how to draw a cube. So if it's a solid cube, then I guess you can't see this thing coming down. But it's like a die from a Monopoly game, or it's like a milk crate. If you were to talk about this as being the regular face, you would take the area of this and multiply by the length. But to find the area of that face would involve taking the length times the length, and then you're going to multiply by the length. And again, I'm going a long way to explaining that the volume of a cube is L cubed. But I thought I would take this opportunity to explain that to you so that you understand what this is saying. Okay. All right, so the volume is equal to L cubed. Now we're ready to differentiate. dv dt equals 3L squared. That's how you differentiate L cubed. But then we need to multiply by the derivative of L, which is dl dt. And the hard work is basically done here. Now you need to start putting numbers in. We were trying to find dl dt, so I can put in the 144 for dv dt. I can put in the when statement. It says if the edge length is 4 centimeters, which means that's the point in time we're talking about. So I'm going to put 4 here, and this is dl dt. So we're going to end up having to take 144. Correct me if I'm wrong, but I believe this is 48, 3 times 4 squared. So you're going to have 144 over 48, which is 72 over 24. Is it 3? No, it is. Works out to 3, eh? So what we end up getting is dl dt equals 3. Now you have to go back and look at what units you need. You had volume in centimeters cubed per second. The length was centimeters. You may even see that if you were to take the centimeters cubed per second and divide by the centimeters that are going to come out on the right, you're going to get centimeters. Actually, this would be squared because it had L squared in there. Divide by centimeters squared, you'll get centimeters per second. But I don't think that kind of unit analysis is necessary. Is that okay, Marcel? Okay. Other questions? And Demi and Nicole, just help me out here. Thumbs up if Zach is there. Thumbs down if he's away today. He's away. Okay, thank you. Any other questions from anyone? Go ahead. Yep, absolutely. So this is the more abstract question, this one, right? And there's no context here. You're just given a relation between x and y. You're told that dy dt is 6, and you're asked to find dx dt when y is 2. So when I differentiate this, let me back up. The rules or the steps I've told you is make a list of the rates of change you know or want to know because you need an equation relating the variables that are in those rates of change. So we need an equation relating x and y. Well, we have one. It's given to us. So basically what I'm saying here, JV, is that step 1 is done. There's step 1. It's just representing the information in the question. Step 2 is to differentiate, but don't make the mistake here, and it is a common one, to kind of jump the gun and just start randomly differentiating stuff. XY squared is a product. So you have to use the product rule. This is the first. This is the second. Derivative of the first is, now here's a really common mistake. Is the derivative of the first 1? No, see, you go away from the fact that there's no context here and you almost fall back into what we were doing in the previous unit. It's 1 dx dt. We're differentiating everything with respect to time. So the derivative of the first is dx dt. The second is y squared, plus the first, which is x. The derivative of the second is 2y dy dt. And this equals the derivative of 12, which is 0. So we're differentiating with respect to time. And I can really see, looking at this question, let's face it, if you saw xy squared equals 12, and you go back to the previous unit and I say find dy dx, you're going to say the derivative of x is 1. But we're not finding dy dx. We're finding dx dt, dy dt, all of these things. Does that second step make sense to you? Okay. I think you could probably answer it. We need to put things in here. This is actually a really good question, and I'm glad you've asked it. There's something we can get out of this. I'm going to start putting things in to find dx dt. I have to put in y. It says y is 2, so I have to put y squared. Plus, now I run into it's a little bump, but it is a bump in the road. I have to put in x, but it doesn't say when x is something. But we are told that x times y squared has to give you 12. So if y is 2, then x times 2 squared has to give you 12. This is just a detour we have to make temporarily. I guess that's what detours are. Before we get back on track, we have to calculate x. Yeah, of course. So 2 squared is 4. 4 into 12 goes 3 times. X is 3. Now we can pull back onto the highway and put a 3 here. Put 2, our y, which is also a 2, dy dt. Oh, we know dy dt, don't we? It's 6. And I realized that we knew that because then I stepped back and looked at my equation and I had 2 rates of change. Now I'm going to solve that for dx dt. Of course, this JV and everybody, the 3 times the 2 times the 2 times the 6, which I think is 72, we have to subtract to the other side where it becomes negative, and that's pretty important. It is 72, isn't it? Okay, good. So we end up with dx dt multiplied by 2 squared, which is 4, plus 72 equals 0. So I can move the 72 over. Now I have 4 dx dt equals 72, and divide negative 72, and divide both sides by 4, and get what I believe, my head is screaming 18, negative 18. And there's no, I like these questions because I think they have you understand the pure mathematics of it, but I don't like them because I don't know what units we should put here. I guess maybe what we should put is units per second. What's a unit? Since it's dx dt, a unit is that far on the x-axis from the origin to 1. And I'm also going under the assumption here, everybody, that dy dt equals 6 with 6 units per second. Is that okay? Okay. Other questions? All right, the goal over today, tomorrow, and Wednesday is to do a couple more examples every day. And hopefully they will get you used to all of the different types of related rates problems that you could expect to see on an exam in this course, and you will definitely encounter next year. The difference, again, next year if you take calculus is that you will go into a calculus lecture. You might have one lecture on related rates, and they might show you 2 examples, and then there's all these other things you have to be able to apply. So let's read this question together. Bill, nicknamed What's the Big Deal McGinty, is the captain of the oil tanker HMS Slick. And he's opened up his Burger King Super Poke Meal, and he's got the really rare Noibat Pokemon card. And he's freaking out, and he slams into the coastline, not paying attention. This puddle spreads in a circular area, and the area is increasing at a constant rate of 6 square miles per hour. And that's when you have oil on water. As long as the oil is coming out of the tanker at a regular volume per hour, it will spread out to a uniform thickness, and the area will increase at a constant rate per hour. Doesn't really matter how big the circular puddle or pool is, it will have a certain thickness. That has to do with the viscosity of the oil. So how fast is the radius of the spill increasing when the area is 9 miles? After you sort through all of the word salad, this is a question we've already done. We did an example with dAdt and drdt in class. We did one example that Liam had asked about the ripple spreading out. That was a dAdt, drdt question. So the difference is this is a word problem, and there's another difference that we're going to have to deal with here. So if we make a list showing what we know. It says dA dt is 6 square miles per hour. And I really believe that these steps, these 3 steps, are required. We're also asked to determine how fast the radius is increasing. Let me just get rid of this from last year. We're also asked to determine how fast the radius is changing, so that's dr dt. This is really not a difficult question. It's actually a really good one to recap the steps. Your first step is not complete until you write out the equation relating those variables. What variables are we referring to here? We are referring to the area of the spill and the radius of the spill. So what's the equation relating those? A equals pi r squared. And we're ready to proceed and answer the question. dA dt equals 2 pi r dr dt. So again, I'm treating this as a, I'm not treating it this way. It is a constant times a variable to a constant. I use the power rule. I wrap that 2 around the variable, which is r, multiply the 2 by the pi to get a new coefficient of 2 pi, drop 1 from the exponent on r, and multiply by dr dt. And now I'm going to go ahead and put in the numbers. So dA dt is 6. We have 2 times pi. Now we have to put in the radius. But this is maybe what differentiates, no pun intended, what differentiates this example from ones that we've encountered so far. Your detour is a little bumpy at this point because it's going to involve irrational numbers. It says when the area is 9 square miles. Well, we know the area formula is A equals pi r squared. So if I put 9 in for A, I have a formula that I can use to find the radius. And I guess what I'm going to have to do is take 9 divided by pi, and then take the principal square root. I don't need to worry about plus or minus here because a radius is a positive thing by definition. And the square root of 9 is 3. So the radius is 3 over root pi. And I'll just point out to you that at this point in time you have the answer. You could use your calculator. Maybe that's what we'll do first. Let's get an answer. Let's get a decimal answer. Let's simplify this 2 pi times 3 over root pi as a decimal, and then we're going to divide it into the 6 to get an answer. So I have 2 times pi times the square root, times 3, divided by the square root of pi. So I'm just simplifying the number set that's being multiplied by dr dt. And I'm getting 10.63. Anybody else get that same number? Okay, so what we're left with now is that 6 is approximately equal to 10.63. It's not exactly 10.63 because pi is an irrational number. Never mind the square root of pi. dr dt. So as an approximate decimal answer, dr dt here is going to be equal to about 0.6 when we divide those. Well, 0.56. So about 0.56. And this would be miles per hour. I just had to go back and look at what we had for the units of dA dt. And what I will tell you is, for Math 31, that's good enough, okay? I made this decision last year. I'm not going to hold you up to some kind of standard where we have to get an exact value for related rates, because they get very messy. But I will show it to you in case you want to know or need to know for next year. With something like this, if I have 6 equals 2 pi times 3 over root pi, 2 times 3 is 6. I also have my dr dt. I shouldn't leave that out. 2 times 3 is 6, and I have 6 on the left and 6 on the right. So if I divide both sides by 6, I'm left with 1 equals pi over root pi dr dt. Well, to get dr dt by itself, this is not a difficult thing. I don't want it to detract from what we're really worried about here, which is the calculus. I'm going to multiply both sides by root pi and divide both sides by pi. So the root pi was on the bottom. I moved it to the top by multiplication. Then what I'm going to do is say dr dt equals pi to the half over pi to the 1. And I can subtract the exponents and get dr dt equals, well, pi to the negative half. Or how many of you would just cancel a half and say 1 over pi to the half? The bottom line is this works out to dr dt equals 1 over root pi, which is really a surprising result. I mean, it doesn't always have to work out that cleanly. The only reason it really did was because the 6 on the left canceled with the 6 on the right. Well, I guess we could double check it here. You can take the square root of pi and then take the reciprocal of it. Better get that answer. Every year I have students, and I don't mind this. So if next year you find yourself in the same boat, that's fine. I have students who email me, Mr. Way, I'm sorry to bother you. I'm taking calculus right now. I have this problem and I can't figure it out. And sometimes it's simple stuff like this question, and they're given that the answer dr dt is 1 over root k, and they're asked to determine the value of k. So you have to go through that procedure. Again, everybody, the decimal value for related rates is good enough here. Any questions with that example? Thanks for letting me know, Zach. Okay, now the last example today, and this is a classic related rates problem, and it appears to many students as if there's a real simple way to do this type of problem, and there just isn't, okay? So it needs to be done in a very specific manner. This is a continuation of the adventures of Captain McGinty. At the moment of impact, when this puddle starts spreading, there's a Coast Guard patrol boat that's 360 miles south of the HMS Slick. Now, one of the things you're going to have to contend with related rates problems is when you draw a diagram, it has to be a diagram showing the situation at any time, not at the beginning. I mean, we can start drawing this and say that at the beginning, this is where the HMS Slick is, and at the beginning, at the instant of impact, this is where the Coast Guard patrol is. But we can't use that picture to come up with an equation. You don't even know right now what the equation has to do, but we can't use that to describe what's going on. That's just one point in time that's at the beginning. What else does it tell us? The Slick flees west. So I always, when I do this on the board, I get my west and east mixed up, but west is to the left on a map. So the HMS Slick travels in this direction. And the Coast Guard boat travels north. Now, before I draw in the north, I want you to notice that the Coast Guard patrol boat is traveling faster than the fleeing captain's boat. So when I draw an arrow indicating the motion of the Coast Guard patrol, I'm going to intentionally draw it longer. And I'm going to mess up this diagram. I don't want you to. But I want you to understand that the lengths that I drew those arrows at are totally arbitrary, because I could have drawn the situation 5 minutes after it started, in which case it might look like that. Or I could draw it a different time later, and it might look like this. Or I could, and please don't draw this, I could draw it like that. And even though everything's been reflected kind of vertically and horizontally here, the math that we're going to develop here would still be useful. Okay? I think it's easier to draw it so that we can construct the right triangle. Now, let's take a breath here. This is just a picture showing what's happening. We need to label some variables. So first of all, what is the rate at which the distance between the two ships is changing? Well, that's that. The distance between the two ships at some later time is the distance connecting the tips of those two arrows. We need to call that something. Let's call it, you might notice Y in a second, but I prefer to call this Z. So we're going to find dz dt. We have two other variables here. This variable, which is only the length of that arrow, I'm going to call Y. And I want everybody to read the question carefully. Look at my diagram. And figure out what dy dt is equal to. So Y is the distance that the Coast Guard patrol boat travels up to a certain point in time, and I'm asking you to find dy dt. Tyson, do you know? No? Grant, do you know? No? Zebi? It's 120 miles per hour. Because that distance y, that's right, that distance y is how far, that's a distance, right? That's how far the Coast Guard patrol boat is traveling. And if I say if y is how far it travels, what's dy dt? Dy dt is how fast it's traveling. It's the rate of change of distance with respect to time, which is speed. So dy dt is 120. If I label this as x, that's also a variable. And I hope you can kind of see that I'm moving towards a Pythagorean triangle here somehow. Liam, what do you believe dx dt is if I call this top distance x? Yeah, it's the speed of the HMS Slick, 100 kilometers or miles per hour. You said 100, right? Yeah. So dx dt is 100. This is what I meant earlier when I said, and we're not even done step one. Step one now is to come up with an equation relating z, y, and x. So we're not even done step one yet. We still have to come up with an equation relating them. And that's why I said earlier, step one is usually the most difficult. I want to point out to you that what most people do when they see this question is they go, oh, x squared plus y squared equals z squared, and they will get the question wrong. Because this is not y. Your triangle, the Pythagorean triangle, is this. That's the Pythagorean triangle. So yes, the hypotenuse squared, z squared, does equal x squared plus whatever that green distance is squared. And that's the final question that we have to get the answer to before we can proceed. What is this distance equal to? Arden, I have a feeling you know. It's not y, actually. And the reason it's not y goes back to that thing that I had mentioned earlier, that where I ended up drawing these two arrows to was arbitrary. I could have drawn those arrows longer or shorter. So it is, this green highlighted area is a variable distance, but it's not y. Farhan? It is 360 minus y because this entire distance, I know it's a color overload here, but this entire distance was 360 miles. So that means that this distance, which is y, plus this distance have to add up to 360, or you can just subtract y out of 360. I think that's probably how most people will think. This is 360 minus y. And that is what goes into the Pythagorean relation. And again, if you just think it's x squared plus y squared equals z squared, you're going to get the question wrong. There are some real crafty ways to get around this, but my experience is to do it the proper way, which is this way. So that's step one. Now we're ready to differentiate. And this specific question, you're going to see many examples like it. You're probably going to get an assignment here, maybe tomorrow, but probably Wednesday, that's a related rates problem similar to this. You have to set it up so that you show the objects, whether they're ships or planes or trains or whatever, and the diagram has to show where they start and the directions they move in, and from that you build a Pythagorean triangle somehow. So, and I know from experience this is the case, that you're not looking at this and going, oh yeah, I got this. Because most people won't. It's going to take some practice. Further examples. So I differentiate. The derivative with respect to time of z squared is 2z dz dt equals 2x dx dt plus 2 times 360 minus y, we drop one from the exponent, times the derivative of what's inside, and here's a common mistake. Ben, do you know what's wrong there? Oh. Huh. Yes, it should be. That's not the mistake that I intentionally put. That was a mistake that I genuinely, honestly made. So it is dz or dy dt, but what else? It should be negative. Thank you. That's funny. So now we're ready to roll and put everything in. I don't see the need to make things unnecessarily more complicated. If everything is multiplied by 2, why don't we just divide both sides of the equation by 2? So now, I think the only thing that's going to prevent you from getting the right answer is a lack of organization. Because you have x, you have y, you have z, you have dx dt, dy dt, dz dt. So going left to right, well, boom. Right out of the gate, we don't know z. Okay, let's just leave that blank for the time being. We're trying to find dz dt. Now, what is x? Why? Yes, correct. Why is x 200 miles? Where'd that come from? Right. It says after 2 hours. And dx dt was 100 miles per hour. So the HMS Slick is moving west at 100 kilometers per hour. If we wait 2 hours, it will have traveled 200 kilometers. I keep saying kilometers, and I'm sorry. It will have traveled 200 miles. And while we're up here, we might as well just put that y after 2 hours will be 240 miles. Okay, so we can put in x. X was 200, or is 200. dx dt is 100. This is what I mean by the only thing that can hold you back from the answer here is lack of organization, because I almost put 120 for x, for dx dt rather. And then we have equal or plus 360 minus y. So after 2 hours traveling at 120 kilometers per hour, y will be 240. So minus 240 times negative dy dt, which is negative 120. And I'm going to just pause there. Don't question why this is going to work. Sorry, it's not negative 120. Yeah, it is. It's negative dy dt. It's tricky stuff. Dy dt is not negative, but negative dy dt is negative. Don't question why this is all going to give you the right answer. It is. When engineers set up cranes, they use related rates for problems where you have one part of the crane moving up, the other part of the crane moving to the right, and they have a cable connecting the two pieces, and that cable has to keep a constant tension. And if they don't change the rate of change of the cable appropriately, disaster happens. Well, this is how they calculate how quickly to reel in the cable, or how quickly to let the cable out. Well, we're missing Z. Z is holding us back. So how are we going to find Z? We could find X by looking at the rate of change of X in 2 hours. We could find Y by looking at the rate of change of Y in 2 hours. But how do we find Z? And I'll give you a hint. The answer is on the board right now. Ben?
You input the values of X and Y value.
Right. This is, and it's why I group this example with the previous one. In the previous one, you were told, I can't remember the number, was it 9 square miles in the previous question for the area? So you were told the area in the previous question. You had to go on this little bumpy detour to find the radius. Here, guess what? We got to put it into four-wheel drive because we're going on a very, very bumpy detour. We're going to put the x and the y into that equation of z squared equals x squared, which is 200, plus 360 minus y squared. Y squared was 240. And then we can find z squared. And take the square root to find z. So $360 minus 240 gives me, well, 120. I have to square that, and I have to add 200 squared. So the square root of 54,400 is the answer for Z. Well, we can put that up there. I didn't leave myself enough room, so I'm just going to do this. Bottom line, everybody, is dz dt is going to be equal to this divided by that. So I'm going to calculate what the value of that yellow highlighted section of numbers is. 200 times 100 plus 360 minus 240 is 120 times negative 120 gives me this number, 5,600 over the square root of 54400. I am not going to simplify that in this question. Next year you'd be asked for an exact value in simplified form. You would have to take the square root of 54,400 and break it up into perfect squares and write it as a mixed radical in simplest form. I don't care in this course. After this lesson is over, I'll quickly show it to you if you're interested. Bottom line, did you also get 5,600 by the way? Okay, so now I have to take 5,600 divided by the square root of 54,400. At that point in time, dz dt is 24 miles per hour. Now, admittedly, this isn't maybe a real-world application of calculus, but it's what we do in this course and in university to try to give things context. In reality, it would probably be pieces of a crane or some other machine where we have a cable. And by the way, final comment, since we got a positive rate of change here, that means at that point in time, they're getting further away from each other. But there might be a different point in time where they're getting closer together. It's a strange thing. Okay. Any questions with that last bit of business of putting in all of those numbers and calculating Z on the side? This will be on your exam. And I would go so far as to say, I don't think there's too many related rates questions that I wouldn't expect you to be able to do in this course. If we do encounter one, I'll make a point of saying, we'll do this one, but don't worry about it too much because it's probably not going to be on the exam. On page 145, 9, 12, and 13, if all you do are the additional problems, none of these additional problems have any of these. Joe and Dave driving in different directions, ship A and ship B. So make sure you do at least one of those from 12 or 13.